Welcome to the presentation of our work, Zero-Shot Image Harmonization with Generative Model Prior. When confronted with a foreground image and its corresponding semantic mask, our task involves extracting the foreground object. Subsequently, placing this foreground object into a given background allows us to construct a composite image. However, this composition process often introduces challenges related to color space and consistency between the foreground and background regions. Image harmonization addresses this issue, ensuring the alignment of color spaces in the composite image. Typically, existing image harmonization methods heavily rely on extensive segmentation datasets for creating synthesized composite images during training. These methods involve applying color transformations to semantic regions to generate the synthesized composite images. While incorporating more transformations enhances the model's robustness in real-world applications, it also results in a larger dataset and higher training expenses. In our work, we challenge the conventional heavy training approach, asserting its inconsistency with human behavior. Human editors excel in harmonization without extensive training on composite images. Over our lifetime, we've internalized the distribution of natural or real images, forming what we term the human long-term prior. A composite image, in essence, represents an outlier to this prior. To harmonize such an image, we envision a corresponding inlier natural image and iteratively edit the composite image to ensure its proximity to the inlier natural image. This process relies solely on the prior knowledge of the distribution of natural images, enabling zero-shot harmonization. To delve deeper into our approach, there are three primary steps. In the first step, we identify the imaging conditions of both the foreground and background regions. Subsequently, in the second step, we envision the appearance of the foreground and the emerging conditions of the background and edit the foreground region using tools such as Photoshop. Finally, in the third step, we assess the visual harmony of the resulting image. Following these steps, even individuals without specialized training can achieve satisfactory harmonization results. Here, we present our detailed approach. In Part 1, we introduce the Imaging Condition Description Generation module, corresponding to Human Step 1. Leveraging a pre-trained vision language model, we prompt it with task specifications such as describing the imaging conditions of both the foreground object and background. Subsequently, we input the composite image and mask to obtain the target output, which includes the object name, foreground description of the imaging condition, and background description. Moving to Part 2, we detail the foreground region harmonization module, aligning with Human Step 2. To approximate the human prior of the distribution of natural images, we reference the pre-trained text-to-image generative model Stable Diffusion, extensively trained on natural images. For editing software, we adopt recent prompt-to-prompt editing technology, complemented by specific harmonization operation designs. The generated descriptions from Part 1, along with the edge map, are inputted into the model to produce a more harmonized image. Within the harmonization operations, we introduce a text embedding refinement module to optimize the text embedding for improved representation of the imaging conditions of the foreground and background. Additionally, a content structure preservation module is designed for foreground structure preservation, consisting of two submodules. First, we utilize the self-attention map in Stable Diffusion to preserve high-level structure. Second, we employ edge maps to retain low-level edge details. Proceeding to Part 3, we outline the performance evaluation module, corresponding to Human Step 3. We train an evaluator to assess the harmonized image generated by Part 2, providing a harmonization score. Based on this score, the approach deduces outcomes like human beings, either breaking out or regenerating the description in Part 1, or continuing iteration in Part 2. This iterative pipeline leads to increasingly harmonized images and, ultimately, the best result. In summary, the pipeline involves the following steps. Alongside this, we showcase results of our zero-shot harmonization, demonstrating compelling performance across diverse backgrounds and objects. Thank you for watching our presentation.